Okay, this is Chapter 11, Section 4, Tree Diagrams. It says, being able to determine the number of outcomes when multiple experiments are being performed is essential to our understanding of probability concepts. Throughout this section, we will explore many real-world applications that involve both the fundamental counting principle and tree diagrams. Such applications may appear in a wide variety of occupations. All right, so the fundamental counting principle is if a first experiment has m distinct outcomes, or a second experiment has n distinct outcomes, the two experiments in that specific order have m.n distinct outcomes. Okay, so looking at example 1, it says if two cards are drawn from a standard 52 card deck, determine the number of possible outcomes if the cards are drawn with replacement. Okay, and then part B is without replacement. So what happens is with replacement, then every time you're drawing from a deck of 52 cards. Okay, so the number of ways to draw two cards with replacement is 52 times 52, which is 2007-04, because the first 52 represents the M, the first card. The second 52 represents the N, the second card, and you're multiplying. It says without replacement, then what happens is you have 52 for the first one, because that's how many cards are in there, but you don't replace the card you draw out. So it now becomes times 51, which gives you 2,652. So this is replacement. It's going to be 52 both times. This is without replacement, meaning the card you drew, you're not putting back. Now, tree diagrams look something like this. And so as a consequence, this particular example here, you have an outcome of H, you have an outcome of T. Okay. Possible outcomes from the die. Okay, so for the first roll, you have 1, 2, 3, 4, 5, 6. If you combine those, that's where we get the H1, H2, H3, H4, H5, H6. The second roll deals with T. And again, we have 6 sides to the die. So it comes 2, 1, 2, 2, T2, T1, T2, T3, T4, T5, T6. We come over here. There's the first example problem. It says a radio station has 2 tickets to give away to a Monster Jam truck rally. It held a contest and narrowed the possible recipients down to 4 people: Christine, Mike, Larry, and Phyllis. Christine's represented by a C, Mike by an M, Larry by an L, Phyllis by a P. The names of these 4 people will be randomly selected from a hat, and the 2 people selected will be awarded the tickets. It says determine the number of sample points in the sample space, construct a tree diagram and list the sample space, determine the probability that Christine gets selected, determine the probability that Christine is selected, then Mike is selected. So first of all, it says the first selection would be a 4, because you got 4 individuals. But we're not replacing, so the next selection would be out of 3 individuals. So 4 out of 3 is 12. So there's our sample space, 12. Come down here, our tree diagram. From the point, we got C, M, L, P. And then C can pair up with M, L, and P. M can pair up with CLP. L can pair up with CMP. P can pair up with CML. So there's our possible outcomes, and you'll see that we have 12. Okay? So then it says, if we know sample space we can compute, it wants to know probability that Christine is selected. Okay? So what we have to do is look at the possible combinations of Christine. So we come back up to our tree diagram. Here we have 1, 2, 3, 4, 5, and 6. So we have 6 possible combinations with Christine out of 12. So she's got a 50% chance of being selected. Then we're looking at Christine and Mike being selected. So if we look at that, here's Christine and Mike. Here's Mike and Christine. but they want Christine selected first and Mike selected second, so it's really only 1. So this one doesn't count. Okay? So it's 1 out of 12. Okay? Here's another example. It says, at Top's Diner, each lunch special consists of a sandwich, a salad, and a beverage. The sandwich choices are roast beef, R, ham, M, H, turkey, T. The salad choices are macaroni, M, and potato, P. The beverage choices are coffee, C, and soda, S. So what happens here is we're going to use our trig diagram. We determine the number of different lunches specials offered by this restaurant. Construct a tree diagram and list the sample space. If a customer randomly selects one of the lunch specials, determine the probability that a roast beef sandwich and a soda are selected. And then it says if a customer randomly selects one of the lunch specials, determine the probability that neither macaroni salad nor coffee is selected. So first of all, we have 3 choices. So it's 3, 2, and 2, which is 12 possible outcomes. If we list those, R, H, and T, for our roast beef, our ham, and our turkey, and then we have here our salad, MP, 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 and we have our beverage, CS, and CS. So see, look what happens. Here's our sandwich. So the sandwich gets selected first. Then when the sandwich is selected, each sandwich has the possibility of selecting a different salad. And then once a salad is selected, each salad has a chance of selecting a different drink, coffee or soda. So here are the possible outcomes. So you got RMC, you got RP, or RMS, you got RPC, and you got RPS. Okay. And then you got the same thing here and the same thing here. Okay. It says letter C, if we're looking for a roast beef sandwich and soda as selected, so we're looking for roast beef and soda. So there's 1. And let's see here. There's roast beef and soda. There's roast beef and soda. So there's only 2. So 2 out of 12 is 1 out of 6. And it says neither macaroni salad nor coffee are selected. So we're looking for no M, no C. So there's 1. There's 2. There's 3. So there's 3 of them. So it's 1/6. Now, probability of an event happening at least once. The probability of an event happening at least once can be determined by the following formula. 1 minus P, the event doesn't happen at all. So what you do is 1 represents 100%, where P represents the probability that all the other events happened.